Magnetism.
Right hand thumb rule.
You see this conductor on screen? If you know the direction of the current through this conductor, well, you can find the direction of the magnetic field. How? Well, hold a wire in your right hand and hold it in such a way that your thumb points in the direction of the current. Fine? Now the direction of the curvature of your fingers. Yes, the direction of the curvature of your fingers will give you the direction of the magnetic field around the wire. And this rule is known as Maxwell's right-hand rule. There is another version of Maxwell's right-hand rule, and it is known as right-handed screw rule. Now, what it states is, if the direction of the linear movement of the screw gives the direction of the current, then the direction of the rotation of a right-hand screw represents the direction of the magnetic field. Think about it. It's actually one and the same. Now take two wires. Let's place them side by side at a certain distance. Now let me show you the direction of the circular magnetic fields around both the wires. Now, based on the rules that we've discussed, can you label the direction of the current flowing through these wires? Think about it. I'll give you 5 seconds. Now the answer. Here is the direction of the current.
Pattern of magnetic field produced by a solenoid.
Due to a solenoid. Solenoid is a device which is similar to a spring. A spring has a continuous loops and moving forward in a given direction. When this is connected to a battery, it behaves as a current carrying solenoid. In a given example, you can see the battery. The positive terminal of the battery is connected to this end and the negative terminal of a battery is connected to this end through a key. When we close this key, the current flows through this and makes a loop in a given solenoid. Each loop in itself creates a magnetic field around the circular loops of itself, which joined together further produce a strong magnetic field around itself and also inside. The inside magnetic field is simply straight lines moving in the direction of the current. As we can see here, the current is moving in this direction. Positive terminal is here. It makes a loop, moves forward, comes back to the negative terminal. So whatever the direction of the current in a solenoid will be the same direction of the magnetic field inside the solenoid. But outside the solenoid, it will make circular loops. Seems to be originating from the negative terminal, or you can say the side which is connected to the negative terminal, and terminates at the side where the positive terminal is connected. Same happens on the below side. This overall solenoid behaves as if a temporary bar magnet. Temporary because whenever we switch off the current, the magnetic field will disappear. And bar magnet because the bar magnet has the similar kind of magnetic field line which originates from one point, makes a complete loop and terminates at the other end. So if we compare it with the bar magnet, this side that is connected to the negative terminal will behave as a north pole, and the side which is connected to the positive terminal will behave as a south pole. So we can write this as north and this as south. This was the complete description of magnetic field produced by a solenoid. Magnetic field lines due to a straight current carrying wire. Any current carrying wire going to produce a magnetic field due to it, and straight current carrying wire is not an exception. Whenever there is a straight wire carrying current, it will going to produce magnetic field lines which will be circular and enclosing the straight wire. Here we have the two examples in which the direction of the current is opposite. In the upper image it is going upward, and in the lower image it is going downward. The circular loop also changes its direction with the current carrying wire. If the current is moving downward, the direction of the loop will be clockwise. And if the current is moving upward, it will be anti-clockwise. This direction is given by a right hand thumb rule. Imagine your right hand holding the wire in such a way that the thumb gives the direction of the current. Then the curled fingers will give you the direction in which the magnetic field lines going to make a loop. As you can see here, the fingers are making an anti-clockwise loop, and so does the magnetic field line.
Magnetic field pattern and experiment setup.
Check the direction or the magnetic field line using a simple experiment. Here is the experimental setup. We have a wooden board on which a lot of iron filings are placed in an arbitrary fashion. There is a compass and an iron rod which is connected to a battery so that the current can flow through it as if this iron bar is an current carrying wire or the straight current carrying wire. When the current is allowed to pass through it in a given direction, the iron filings adjust themselves according to the field line. As we can see here, the magnetic needle also shows a deflection which is tangential to one of this loop. The magnetic compass gives us the direction whether the loop is clockwise or anti-clockwise, and the iron filings tells us that indeed the magnetic field lines along a straight current carrying wire will be circular. In this particular case, you can see the direction of the current is upward and the loop is anti-clockwise. If we reverse this direction, the loop's direction will also going to be reversed.
Electric bell.
You see this electric bell? How does that work? Look at it carefully. What do you see? It has a piece of iron wound in a coil of electric wire, and there is a hammer. Now this can hit a metal gong, but the hammer is not in contact with the gong. You see that? Now the hammer is attached to the tip of a screw through a flexible metal strip. There is a reason for that. Now let's see what happens when we turn the switch on. The bell is ringing. How did that happen? Look at it again. When we switched it on, the current started flowing through the coil of wire. Now because of this, the iron object, you see that? It became an electromagnet. So the metal hammer got attracted towards the electromagnet and it struck the gong to produce a sound. But the moment the hammer got attracted towards the magnet, something happened. And what was that? It lost contact with the iron screw. The circuit was broken. And once that happened, well, our iron object was no longer an electromagnet. So the hammer went back to its original position. Once that happened, the metal strip touched the screw. And because of that, the current started flowing through the circuit again. Once again, the iron object became an electromagnet, and the cycle gets repeated in an electric bell. So whenever the circuit is closed, the hammer strikes the gong repeatedly to produce sound. I'm sure now you know how an electric bell works.
Let us perform a small experiment.
See on your screen is a current carrying wire. And there is a compass needle. Let me bring this compass needle close to this current carrying wire. What happens? You saw the deflection? Why did that deflection happen? Before I answer that question, let me take you back in history. Have you heard of a gentleman known as Icse? He conducted a very simple and ingenious experiment and demonstrated something very interesting. Let me try to replicate that experiment for you. Look at this. You see this electric circuit? Great. Now what we need to do is, we take a magnetic compass, and that you can get from anywhere, and bring it close to the section of the circuit. Hold on. The switch, as you can see, is open. So let's close the switch. What do you observe? Yes, As soon as you close the switch and the circuit is complete, there is a movement in the compass needle. And that's exactly what Oersted suggested. And this is the phenomenon that is known as magnetic effect of current. So, when electric current passes through a wire, it actually produces a magnetic field around it. Once it does that, it starts behaving like a magnet. So when you get a compass needle close to it, well, that's why you see that deflection. So that answers our initial question.
Fleming's left-hand rule.
Take a thick copper rod, suspend it with a support. Fine. Now connect its two ends with a simple electric circuit. You see that? Great. Now bring a horseshoe magnet near this rod, and carefully, it has to be in such a manner that the copper rod lies between the two poles. Fine. Now allow the current to flow through this rod. All you need to do for that is switch the circuit on. And what do you find? The suspended end, that is the lower end of the copper rod, moves rightward. Why did that happen? You know, when a current carrying wire is placed in a magnetic field, it experiences a force. So we can say that the rod got displaced because the current carrying rod experienced a magnetic force in which direction? The direction perpendicular to its length and the magnetic field. Now let's do something. Change the direction of the current through the rod by changing the polarity of the battery. Fine. Once again switch the circuit on. What do you see now? Once again there is a displacement of the rod, but the direction is opposite this time. Let me ask you a question. Do you think there is a relation between the direction of force experienced by the rod and the direction of the current that goes through it? I will not answer that question. Think about it.
Functioning of electric motor. Electric motor is a device which converts the electric power source into a mechanical rotation. It is used in variety of apparatus. We will first start with its construction. This construction is simple. It contains one circular loop that carries a current released from the power source or the battery. This electrical circuit is connected with the carbon brushes and a split ring commutator. The split ring commutator has a rigid connection with the circuit, but the carbon brushes do not contain any rigid connections with the commutator. The rigid connections are not there because it facilitates the commutator to rotate on its axis without missing any connection with the black carbon brushes. This helps us in providing the continuous current and also making the circular loop rotate on its axis easily. Second, the circular loop is placed in a parallel magnetic field. The parallel magnetic field is created by two strong magnets placed in such a way that north of the first magnet is exactly facing the south of the second. This is the simple construction of a DC motor. Electric motor. This is a symbolic circuit diagram for an electric motor. Electric motor, as we know, is a device which converts the electric power into the mechanical work. When we supply the electric current through an electric motor, current passes through the given circuit. This circuit is placed inside the magnetic field, and on the first arm, the current's direction is from down to up, and the magnetic field direction is perpendicular to current. If we apply Fleming's left-hand rule, we can easily find out the direction of the force, which will be upward direction. The situation will be reversed on the other side of this electrical loop. The current will be in downward direction. Magnetic field will have the same direction perpendicular to it, and the force this time will not be acting upward, but it will be acting downward. Because of this equal and opposite force, this electrical loop will now rotate in a clockwise direction. The moment it rotates, this loop reaches to the other side and the first loop reaches to the second loop position. The current direction reverses in this and the rotation continues. This rotation of the loop is further attached to the pulley, which can be used to extract any kind of mechanical work. The electric motor we use in our home inside a fan or even inside a car to rotate a fan in our home and the wheel of a car are something similar to the electric motor we are studying in this case. The only difference is here we are using a battery, which is a direct current, and at home or inside a car, those kind of direct current is not used, but the alternating current is used. But the major functioning is same, in which electrical power.
Electromagnetic induction.
So, are you ready to make a simple circuit? Well, we need to make a simple circuit using a solenoid and a galvanometer. Now look at the pointer of the galvanometer. Initially, the reading is 0 because there is no current that is flowing through the circuit. Now let's do something. We take a long bar magnet and move its north pole within the solenoid from end P to end Q. Can you see that? Now look at the pointer of the galvanometer. What do you observe? Well, the pointer of the galvanometer deflects in a particular direction. Why did that happen? That happened because a temporary current was set up in the coils of the solenoid when the magnet moved. Now, once the magnet rests in the solenoid, once again there will be no deflection in the galvanometer and the pointer shows 0 once again. Now let's remove the magnet from the solenoid. What do you see while you are removing the magnet? Once again you will see a deflection in the galvanometer. But if you notice carefully, this time the pointer will deflect in the opposite direction, indicating once again that a current has been set up in the coil. Now, what happens when the magnet is stationary but the solenoid is moved across it? You can see that a current is induced in the solenoid when it is moved across a stationary magnet. Now, this shows that the potential difference and the current are induced in the solenoid when either the solenoid or, as we saw in the first case, the magnet or both of them are moving. Now it's definition time. This phenomenon of generation of induced current in a conductor by changing the magnetic field or by moving a conductor in the magnetic field is known as electromagnetic induction. I hope you've understood the process now.
Uses of artificial magnet.
Here is Rajesh. And what does he have? He has a piece of bar magnet and a paper clip. Now he attaches the piece of bar magnet with the paper clip and waits for some time. What does he notice? If he brings the clips now to this paper clip, it starts behaving like a magnet. It is actually attracting all these clips. Now, why does this happen? I will not give you a straightforward answer, but I'll help you discover the answer. Before that, let me tell you how to make an artificial magnet by using a permanent magnet. For that, you need to know what an artificial magnet is. Artificial magnet is a special type of magnet that is made by using a permanent or let's say a natural magnet. And the simplest method to make an artificial magnet is the touch and stroke method. Now, what is this method? Take a small iron bar and a natural magnet. Fine? A permanent magnet, that is. Now, put the iron bar on the table in such a way that it cannot move because of the magnet. Fine? Now, what do? We place one end of the bar magnet on one of the ends of the iron bar. Now slide the magnet along the length of the iron bar till the magnet reaches the other end. Now after that, lift the magnet. Remember to lift the magnet and repeat the process and do it for, let's say, at least 5 minutes. Once you've done that, put a paper clip near this bar. What happens? Yes, the iron bar attracts the paper clip. That is, the iron bar has become a magnet. And of course, it's not a natural magnet, so it is an artificial magnet. And you know something? The strength of this artificial magnet will be much greater if you increase the number of strokes. Now let's do the reverse. Let's try to magnetize the iron bar by stroking the surface of the magnet, that is a permanent magnet, with one end of the bar. Just the opposite, right? What do you notice? Yes, the iron bar does not become a magnet in this case. I hope you've understood the touch stroke method. And I also hope you've discovered the answer to the first question that I asked you.
Magnetic meridian.
Let's first consider a point on the Earth's surface. Now, at such a point, the direction of the longitude circle determines the geographic north-south direction. That's easy. The line of longitude towards the North Pole indicates the direction of true north. The vertical plane that contains the longitude circle on which the Earth's rotational axis lies is called the geographic meridian. I hope you know that. Now, similarly, we can define a magnetic meridian. A magnetic meridian can be defined as the vertical plane which passes through the imaginary line joining the magnetic north and south poles. Now, this plane intersects the geographical meridian. The angle between the magnetic meridian and the geographic meridian, well, that is what is known as magnetic declination, or simply declination of that place. In fact, the declination of a particular place can be found using a magnetic needle.
Geographic meridian.
Well, this is our planet. You know, earlier it was thought that the Earth's magnetic field was due to a giant imaginary bar magnet, which was placed approximately along the axis of rotation of the Earth and deep in the interior. Now, this is very simplistic, and this simplistic picture is certainly not correct. You know, it's true that the magnetic field lines of the Earth resemble the field lines of a hypothetical magnetic dipole located at the center of the Earth, but the axis of the dipole does not coincide with the axis of rotation of the Earth. In fact, it is presently tilted by approximately 11.3 degrees with respect to the Earth's rotational axis. If you look at it in this manner, the magnetic poles of the imaginary bar magnet are located where the magnetic field lines due to the dipole enter or leave the Earth. Now, the location of the north magnetic pole is at the latitude of 79.74 degrees north and the longitude of 71.8 degrees west. It's a place somewhere in North Canada. And what about the magnetic south pole? It is at 79.74 degrees south and 108.22 degrees east. That is in Antarctica. The pole near the geographic north pole of the Earth is called the North Magnetic Pole. And likewise, the pole near the geographic South Pole, well, that is known as the South Magnetic Pole. Look at this. This, I'm sure you've guessed, is a magnetic compass. It's actually a very uncomplicated thing. It is nothing but a small magnetized needle, and this needle is free to rotate about an axis. So once you have such a needle that is free to rotate, you have your magnetic compass. I don't know if you've noticed, but a magnetic compass always aligns itself along the north-south direction. Now, why does that happen? Think about it. Let me tell you something. Opposite poles of magnets attract each other, and like poles, well, as expected, like poles would repel each other. Now take this example. Here are two small toy cars. Let me label them as A and B. Now let's place a bar magnet on top of each car. Can you see that? Yes. Now we bring these cars closer. Leave them. And what happens? Yes. Now let's change the orientation of the car. And once again bring them closer. What happens now? Right. So what have we learned? Yes, like poles of magnets repel each other and unlike poles attract each other. What we have is a bar magnet. The poles obviously you can see. We need to draw the field lines. So let's place our compass. There you go. The needle. Yes, north and south. Let's mark the north and south point. Move the compass. This is the position of the north point. Keep moving the compass and keep marking your points. Once again, the compass moves to the next position. North, there is your point. Now, once we've got all these points, how do we draw the magnetic field line? You don't need my help for that. All you need to do is connect those points and you've got your magnetic field line. This is exactly the process that you have to use for drawing rest of the lines. And we have a beautiful diagram. You see this pin? If I ask you to move this pin without touching it, can you do it? Well, I can. For that, we need a magnet and a sheet of paper. Now hold the sheet horizontally with your one hand and place the pin on it. Now take the magnet in the other hand and move it back and forth exactly below the paper sheet. What do you see? The pin moves, even though you are not touching the pin. Now what actually happens is, the magnet, as you know, attracts the iron pin. So the pin moves on the sheet along the same path as the magnet. And we get a feeling that the pin is moving on the sheet on its own.